Okay, let's attempt the exercises of section 9. Okay, so for the first question, I've actually already mentioned the injective function. It's and that doesn't use choice. So is it? What is it? Yeah. So for every integer, we just have it light up as 1, and that when n is equal to m. So for all n is equal to m, then it's 1 and 0 otherwise. And yeah, that's how we get any function we want. So that's an injection from z plus 2, the set of all functions from 2 to z plus. No, z plus 2. So yeah, first question is done. And for the second one, let's see. Let's see the first part. Collection A of non-empty subsets of z plus. So non-empty subsets. Okay, so every subset of z plus is going to have a finite cardinality, right? It's going to be a finite number. So there's a bijection for every. So yeah, we can have a count. Okay, so let's go step by step. Let's take all the subsets of z plus that have cardinality 0. There's only one, right? And all the subsets of z plus that have cardinality 1, there are countably many, z plus many. And you just go on and realize it's going to be finite, countable the whole time. So we have a countable union of, what do you want again? A choice function, right? Oh, yeah, you just take the least member. You're done. By the well ordering principle, you can take the least member. That's all. I thought it was something. Yeah. For Z, let's see. Yeah, you can also, so yeah, you just make a well order. We'll discuss that later, but essentially every subset must have a least member. And for Z, what you have to do is you can first order them by sign. So, no, first order them by magnitude, which is, if it's 2 or 1 or 2, minus 2 or 1, minus 2 is bigger, right? And 1 smaller. And then among minus 1 and 1, minus 1 would be smaller. So you can, that's the kind of dictionary order essentially, right? And 0 is the least. So with this order, any subset you take, you'll have a least member. And yeah, I don't know if this is proven or not, but yeah, this is a well order and you can check. It's essentially an extension of the dictionary order. It has the same order type, I believe, as 1 comma 2 times z plus, and then you add a least number. So I don't know. How do you add a least number to it? I don't know how to do that, but yeah, maybe this might work out. Yeah. And then you just add one member and it's fine. So you have two cases in the worst case scenario. So yeah. Okay, now for rationals, yeah, you can order them in a similar way as well. Let's see. So you take the reduced form, right, where they're co-prime and there exists one because we've proven it. And well, let's see. Yeah, so you order them by their sum, so m plus n, and then maybe the sign. So if it's positive that way, then it's and otherwise if it's negative. Is that good enough? Yeah, and then if you also need a constraint, then m has to be less than n. Maybe that. Yeah, maybe. Like, yeah, essentially you can order it. It's not that hard. It's also a kind of dictionary order because you're just ordering n comma n, right? So yeah, and we'll discuss later that a well order can be made from a product, so a dictionary order, and that's exactly what we're here. So if you can get a well order, you can get a choice function essentially, which again is proven later. They're equivalent actually. So this is a kind of motivation. Okay. For D, however, we do need the choice function, and to give an idea about how it's any effort you think is useless, I'm just going to take the closed interval 0, comma 1, or even open if you want. So open 01 has the same order type as the real numbers. And yeah, it has the least upper bound property, sure, but any subset does not have the smallest member, right? So how would you choose this choice function, right? We can't do that trick anymore. Let's say we take any small interval, so any open interval, half is not available. So what smallest member will you take? And yeah, even the existence of a well order for the real numbers requires choice. So yeah, it can't be done without choice, but if you have a choice function, then yeah, you just take the choice um, member of any for any subset. So yeah. Okay, question three. So towards a contradiction, let A be finite, right? So that means what? That means A has cardinality n is an integer, right? Okay. Now, how do we show that A doesn't have any cardinality, any finite cardinality? So by induction, we have to show that for all n, A is not equal to n. In fact, I'm going to show it's greater. Yeah. If we show that, then we're done because it's not finite. So that's all we have to show. So yeah, here's the so it's critical that we take fn having being a function from 1 to n and not m or anything else to a. It has to be the same thing because otherwise the proof won't hold. Otherwise, it can actually be finite. You can have a finite set that essentially loops around, right? I think it was. I'm not entirely sure. Yeah. So where was I? Yeah. So let's say if it's m the whole time, well, what's stopping it from being a singular function? And then we could just have a correction of since the index set only needs to be surjective and not injective, you could just have the same set being repeated countably many times, countably infinite many times. Okay. So that's why the n being the same as the index n is crucial. Okay. Now so we assume it has the cardinality equal to n, right? So it's in a bijective correspondence with the section Sn plus one or Sn, I'm not sure. Sn plus one, yeah. Now what? Now, okay, yeah, we know for sure that it there exists m greater than n. In fact, n plus one is such an m, such that f of m is an injection from this to a, right? Okay, so given this injection, what do we get? We get that, well, uh, I think we're going to get a contradiction through a bijection with a proper subset. Let's see. Oh, yeah. Or, yeah, there's going to be an injection from M to the section of N. And that's a problem because this is a proper subset of this. So that's a direct contradiction. And what does that mean? That means, well, this statement is wrong, right? And it can't be less than either because, well, yeah, directly. So, so this is proven, and that's all we needed to prove. So yeah, it's infinite, and we did not need to use choice for this to prove that it's infinite. Do keep that in mind, and that's because we were handed the index set of the functions, and this n is the same as this n. That all of them are crucial. These facts. Now, however, we can't construct an injective function from from z plus 2. That can't be done. So any naive approach, I'll just tell you, f of n is equal to fn of n, let's say. This won't work out because there's nothing stopping this to be the same value each time. There's nothing stopping it. Just fix a naught and define all happen. They can all happen to be the same a naught. at this n value for the function fn. So this naive approach won't work, and there's no approach that would work, and you'd need a lot of arbitrary choices, and the subsets must be chosen carefully. Now, how do you do it with choice? That's another question, and I'll show you that. Okay, so you take all the ordered pairs, fn, uh, fn, yeah, you take the functions union, right? So you'll get all the rules. Now, by the axiom of replacement, I am essentially you can take a function from a function of functions, and you can collect all the ranges. So we have the collection of A such that there exists N, such that Fn there exists M, such that Fn of M is equal to A, right? We can take this collection, right? Yeah, so you take the collection of all these outputs essentially. So it's the collection of all ranges and the union. And you can get this from, can you get this without choice? Yeah, you can get this without choice. Now, once you have this, um, yeah, so simply, yeah, you take any member and you take f z plus to go to this member. Essentially, yeah, you have a choice function from power set of this set. I'm going to call it calligraphic A. Yeah, you make a choice function from calligraphic A to A. And using this choice function, you can simply, since A is infinite, which we've now proven, we're not going to run out of members. F of z plus is definitely going to be contained in A. It might be equal to A, but it's at least contained. And yeah, we just remove them countably. So you take one member, you remove it from that, right? And then you put the choice function again. Then you take another member, you remove it from that, and so on. So that's how you get an injective function from z plus to A. So yeah, you can do it with choice, but without choice. And the key thing to remember is you can't make an infinite number of arbitrary choices. Yeah. A finite number of arbitrary choices seems to be fine. I'm not entirely sure why, but yeah. So this is what we've done here with this power set function, and that's what choice allows us to do. Okay. Yeah, there's a theorem. So I mentioned it earlier, but the countable union of a countable set need not be countable. And the critical step where the mistake was made was assuming that we can have a surjective function for every single n. Again, that's an arbitrary choice because we know that there exists a surjective function, that's fine, but we don't get to choose that surjective function for each n. That's a problem. So choosing a surjective function from for each an is a problem. Everything else was fine, including the index set, the defining of the composite function, all of that is fine. This is where choice was used, and yeah. So to make such a function this time, we would need, let's see, how can we use choice to make it rigorous? So, hmm, let's see. Yeah, you just take the set of all, yeah, you take the set of all surjective functions. Yeah, you take the set of all surjective functions, you choose one of them, and then you remove all the ones with this fixed domain, right? So you choose the ones for A1, you remove them all the surjective functions, then you choose one for A2, you remove them all, and so on. And this is, I think, fine with choice. You can make it even more precise, but yeah, this is similar to the collecting all the ranges. Yeah, okay. Use choice axiom to show that if this is surjective, then it has a right inverse. Yeah, okay. So let's say f from A to B is a surjective function. So that means what? That means for all B belongs to B, F inverse B is non-empty, right? And this is a subset of B by definition. So what does that? Sorry, A. So we have a choice function from power set of A to A. Yeah, so power set is equivalent because, well, it's a collection of sets that such that it's unique, right? So that's why we can use it. Okay. Now, yeah. So this set certainly lies in the power set of A, right? And we can choose a unique member of A such that it lies here. And once you do that, you get the unique member can be defined as the right inverse. So G is equal to P of F inverse B, right? C is the choice function. And this is a unique member, so it's a rule of assignment, and it's the left inverse because it's in the inverse image of B. So this will be let's see, G of B. So what does that mean? That means we're going to get an inverse image, and it's going to be the identity because of this by the definition of F inverse, and that's precisely what we wanted. For defining a left inverse for the injective case, that doesn't require choice, I believe. So let's just check. Yeah, injective, right? So how would we go about it? Let's see. Well, G inverse of any member of B is going to be a unique set. It's going to be a singleton. It has to be a singleton, otherwise it will stop being the inverse image. So yeah, sorry, F inverse. So yeah, this since it's a singleton, you can remove the brackets, which is a unique operation. It gives you a unique output. It's a function from function. It's a function of functions or sets if you want. Yeah, the axiom of replacement essentially wants a unique function from sets to sets. And you can get that. This is very similar to the transfinite definition, sorry, the recursive definition thing. And that's exactly what we're asking for too. But given that, if you can remove the brackets and define it as G of B, you'll get the left inverse. So G O F, you can check for F of G in the earlier one. G O F would be what? Let's see. So it has to be defined. So F of A is defined, and it will be, let's say, D. And G of B will give back F of A because, well, otherwise injectivity is contradicted. So yeah, it's identical. And this didn't require choice at all because there's no arbitrary choice here. There's a unique choice, and we're choosing that very unique one. So yeah. Okay. Most of the right. So do we need choice for it? No, we don't. Okay. We have to show that the power set of A is a subset of A. From what? From okay, it's the set of all sets, right? So hang on. Alpha is the set of all sets, and since power set of alpha is a set which is allowed to be constructed by the properties we were allowed to use, it's okay. Yeah, more precisely. Hmm, so every subset of the set of all sets has to belong. Let's see. This is a bit trickier than I thought. Yeah, so I thought about it, and every single member of let's see. So every single member of the power set of uh, calligraphic A, so I'm going to call it B. It's going to be a subset of this set, right? Now, what we have to show? We have to show that this B has to belong to A, right? But observe that, well, it's a set, right? by assumption, and this is a subset of a set. And we're allowed to make subsets of sets, and they're going to be sets. So because of that, well, it has to be contained in the set of all. So yeah, and that includes alpha itself, right? So yeah, I'll call it alpha. Okay, and this gives a contradiction because, well, look at this. So we already have a theorem that there is no injective function from power set of any set to itself, right? Yeah, but here we can make one, which is the identity function. So that's a problem. Yeah, that's a contradiction, and yeah. Now for the paradox. Theta is the set of all A such that A is in the set of all sets, so A is a set, and A does not belong to it, right? Okay. Now theta does belonging to itself. What does that imply? That implies that if beta set, let's see, it's a subset of yeah, it's by definition a subset. So this belongs to alpha no matter what. Okay. Here it's violating this property, right? Which implies beta does not belong to itself. So that's okay. And let's assume beta does not belong to itself. Well, this implies since beta is a set by definition, uh, let's see. Hang on, is beta it's a subset of A, right? Hmm, would it belong to it? Oh yeah, alpha is this is a subset, right? This is a set, so every subset is going to be a set, so this is a set too. So it belongs here. So that part's fine. Okay. This implies, well, given this and this, we get that beta belongs to beta. So both implies the other. Essentially, this proves that which is a direct contradiction. How can something imply its opposite, right? Like be equivalent to. That's a contradiction. So yeah, that's the paradox. Okay. Yes. So an uncountable set is a set that's not countable, and countable is essentially countably infinite and finite. So if it's not countable, then it's not finite too. So every uncountable set is infinite. And because of that, using a choice function, we can define we can essentially define, let's see. So I'm going to call the set A, which is uncountable, 2A. Yeah. And from this choice function, we can get, well, let's see, we can get choice of A is equal to A naught, choice of A minus A naught and A is equal to A1, and yeah, so on. We can get a function from Z plus to A. What does that mean? That means Z plus is of, sorry, A is of greater cardinality than Z plus. What I have been saying the whole time. Yeah. So if every uncountable set has a greater cardinality than Z plus. So now we just have to show transitivity of this thing. So to show that, well, a composition of two injective functions is injective. So we have an injective function from B to A and an injective function from C to B, and compose them, we get an injective function from C to A, and that's it. That's all we need. Yeah. Find a sequence of infinite sets such that for each space, each AN has greater cardinality than AN. Yeah. I mean, should be infinite sets. Yeah, right. Okay. For infinite sets, it's slightly trickier, but not that hard. Yeah, greater cardinality. So given that power set of A always has greater cardinality than A by the trivial injective function, or this choice, I'm not sure. We have a function from A to power set of A by taking the least member. I think it works out, yeah. How would you do it? Let's see. Well, it certainly should be possible. Yeah, it's okay. Yeah, just think about it. It's not too hard. I think you might not be able to do it without choice. I'm not too sure. So yeah, we'll see that. We'll see about that. You will see about that. Okay. So from that, you can just define A1 to be A, which is an infinite set. So if you want, you can take that plus, and A n is equal to, yeah. So from that, we got an infinite series of infinite sets, and they're infinite because essentially, yeah. So you can, how would you define the infinite thing? Let's see. I mean, it should be trivial, but let's see. Why is it infinite? Okay. So there's an injective function from an to from z plus to an, right? We're assuming by induction, and we have to show that there's an injective function from z plus to an plus one. Yeah, so it comes down to this essentially. You can just compose the functions, right? And to do that, fine, I'll think about it. Hmm, I don't know. Yeah, I was being stupid. So the injective function is just map every a to the set singleton a. So the singleton A is going to lie in the power set of A because it's a subset, and yeah, you just map that. And this is a you can check it's a function if you want. It's a bijective function. It's a injective function if you want. Yeah. So because of that, the inductive step is true, and all of them are infinite. Okay. Find a set that such that for every n has cardinality greater than an. For every n has a cardinality greater than an. Oh, right. You just take the union. That should be fine. Let's see. Is that fine? Well, yeah. So the union is going to contain each set. You can just take the identity function and let's see. Or is it not the union? Yeah, I think it is the union. Yeah. So let's just check. It's going to contain all n for all n, right? So yeah, we have the trivial injective function. And because of that, it's of greater cardinality than an for all n. So yeah, the union. Show that power set of Z plus and R have the same cardinality. I think I skipped over it in the previous section. I'll go over it now. Yeah. Mm, okay. So I'm just going to use what the question has let me use, which is every real number has a unique string of uh, integers, a unique decimal expansion. Yeah. So I'm assuming it's unique. Now, for each unique expansion, we have to make a corresponding subset of that. So how do we do that? Let's see. Subset of it. Okay, we've already established that this has a bijective correspondence with x to the power omega, which is the set of all functions from z plus to 2, right? And this also has the same as the set of all functions from z plus to 10, right? For the set 0 to 9. Yeah. Okay, so hmm, are we almost done? Let's see. So, okay. So if this is agreed upon, then all I need to find is an injective function from R to this set, the set of all functions, right? Then I'll be done. And that's simple because, so this is the case because there's an injective function from Z plus to Z plus. And we established that they have the same cardinality, right? So you can compose the bijective functions, bijections to get a injection. Yeah. Yeah. So for the injections, we need one from X to the this. Yeah, so we have injective functions from R to this as well. Let's see. Hmm, okay, so I'm going to take the set 0, comma 1, and this has the same order type as R, so there's a bijection and it's all fine. And if we take all the decimal expansions, we're going to get a function as, f of 1 is 1, f of 2 is 2, f of 3 is 3, and f of 4 is 4, f of 5 is 4, and so on, right? There is one injection, and for the other one, well, we take a function and is that a bijection? Let's see. Yeah, this might just be a bijection. In which case we're done. Yeah, this itself is a bijection. So there's a little bit of a problem because it's not an infinite thing. There's the non-uniqueness part, but yeah, like it works out. They're outliers, I think. Uh, if you want to think about it harder, then yeah. Hmm. Oh yeah, if you look at how the real numbers are constructed, they're actually constructed through Cauchy sequences, and so they constructed through Cauchy sequences and Dedekind cuts, and both of them are actually a subset of the power set of real numbers. So at the very least, it has the lesser cardinality. And yeah, so like essentially you're taking a cut and which is a subset of the rational numbers, and yeah, for the whole set, you'll have to for the other direction, you have to look at some other place, probably the whole 2 to the power omega to the power omega thing. But yeah, very, very good.